Hello everyone. Today I'm thrilled to bring you an exciting new development in the field towards generating thread-safe classes automatically. This article was the one who caught my eye. Let us dive into the details. In essence, this paper automates the traditionally complex and error-prone process of synchronizing access to shared resources in multi-threaded code. In this work, they propose a method called AutoLock. The main goal of AutoLock is to take a class P as input with its methods and variables, and output a class Q that satisfies three properties: linearizability, deadlock freeness, and efficiency. To do so, AutoLock works in 3 steps. Step 1. Infer how variables are accessed. Step 2. Generate automatically a locking policy based on the observations made during Step 1. Step 3. Automate the code refactoring. Let's review how Step 1 works on a high level. In Step 1, static analysis is performed on the source code to infer access annotations. Access annotations are associated with each variable, private and public methods. There exist 3 types of annotations: immutable, thread-safe, and shared. Immutable means that either it is, for example, an integer or a string, or that it is never updated. Thread-safe means that the variable is implemented to be used in a multi-threading context, for instance, a synchronized array list. And shared means that it must be protected by some kind of lock mechanism. In addition to access annotations, read and write access to variables are identified in the bodies of the methods, and relations between variables are spotted. In general, 2 variables are related if their values depend on an extern function, and their relation is not captured by the previous access patterns. As we will see, a capital point later is that relations are transitive, meaning that if a variable A is related to a variable B, and B is related to C, then A is related to C. Let us see how the locking policy is generated based on these insightful annotations. The generation of locking policy holds 2 basic principles. A mutable variable is always guarded by the same lock, and related mutable variables are guarded by the same lock. The synthesis algorithm works as follows. First, they assign no lock to immutable variables. Second, they compute the set of all relations taking into account transitivity. A fresh lock is added to every group of variables related if there are at least 2 variables in that group. Note that the locking policy is synthesized based on the annotations guessed based on heuristics. Therefore, there is no guarantee on the correctness of the annotations, and consequently, the synthesized locking policy. This is inevitable as we do not have the specification. It is also why the access annotations must be presented to the programmers for validation. The tricky part is to automatically translate the locking policy into actual code. An implementation of a locking policy should follow these requirements. For any mutable variable, the associated lock should be acquired before reading or writing to the variable. The lock should be released only after the variable's last access, and all locks should be released by the end of the method. Acquire and release locks as late and as early as possible, respectively, without breaking other rules. The policy should not introduce lock ordering deadlock. To do so, the paper establishes a global order on locks and adjusts the lock acquire release statements accordingly. They analyze every path the program could take on a graph representation of every possible execution of a method. When a variable on a path of possible execution is read or written before its associated lock is acquired, a new lock instruction is fitted before the read or write, effectively protecting the variable. Now, to decide when to release the lock, they find the nearest last instruction using the variable. To do so, a backward breadth first search, starting from the end nodes of the execution graph, finds the nearest node to the lock instruction, such that the protected variable is not read or written in the following nodes. Lastly, they examine the lock ordering of every execution possible to check whether there is any path which holds multiple locks at the same time, and the locks are not locked in the order predetermined. Now that we briefly reviewed how the proposed method works, let's take a look at the results obtained in various benchmarks. The first research question the authors tried to answer is, how effectiveness is our proposed technique in avoiding the concurrency bugs? The proposed auto-lock technique effectively avoided all concurrency bugs in the tested sample of 12 concurrent programs, demonstrating its capacity to systematically prevent such bugs. The time required for generating thread-safe classes ranged from less than a second to 15 seconds, significantly lower than the average time traditionally spent on fixing a single concurrency bug. The second question is, what is the time overhead of our method? The time overhead of AutoLock was deemed reasonable across diverse program sizes, with an average of 7.54 seconds to handle each program in a larger set of 33 programs. Even for the most substantial program, the total processing time remained under 4 minutes, suggesting that AutoLock could be applied to larger, real-world programs. Finally, the last research question answered is, how efficient are the generated thread-safe classes? The efficiency of thread-safe classes generated by AutoLock was comparable to that of expertly optimized concurrent classes from the JDK library. While expert classes performed best in most read-heavy scenarios, AutoLock-generated classes excelled in a couple of cases, outperforming the baseline version. When only right methods were invoked, AutoLock-generated classes demonstrated the best performance in 3 cases, though slightly less efficient in 4 others. In conclusion, the paper introduces AutoLock, a method that automates the process of generating thread-safe classes to synchronize access to shared resources in multi-threaded code. By leveraging static analysis and access annotations, AutoLock infers how variables are accessed and generates a locking policy based on relationships between variables. The locking policy is then translated into code, ensuring proper acquisition and release of locks without introducing deadlocks. The results demonstrate the effectiveness of AutoLock in preventing concurrency bugs, with significantly reduced time overhead compared to traditional bug-fixing methods. Moreover, the generated thread-safe classes exhibit comparable efficiency to expertly optimized concurrent classes in various scenarios. AutoLock shows promise for improving the development of thread-safe code in real-world applications.